Hello, class. This will be the final recorded lecture for our Trig class, and we're going to do something that is actually, in my opinion, quite important and useful. This is where the polar coordinate system for complex numbers makes arithmetic super easy. And this is the idea of either taking a complex number to a power or calculating the roots of a number in the complex plane. And so let's start by taking complex numbers to a power. That's the easier one to get started with and very powerful one. And so this is this theory of Moivere's where he took the multiplication formula and repeated it over and over again. And you could see how it simplifies when you take something to a power. So if you have a complex number z and you take it to a power like 5 or 8 or 10, you simply take the modulus or the r value to that power, and you take the angles and just multiply it by that. Very, very cool. Very, very easy. And so what I'd like to do now is an example of one that you would never do in the Cartesian or rectangular coordinate system. And it would be a problem that looked like this. Say like we have 1/2 plus 1/2 I, and that is our z value. And say like we want to take z to the 10th power. It's like, oh my, how would you do that? Well, it'd be very tedious, not hard, but very tedious. And you would have to do it over and over again, 9 different times. But if we do this, let's convert it to the polar representation. So r would be 1/2 squared, right? Plus 1/2 squared. And so that would be square root of 1/4 plus 1/4. And what would that be? Be square root of 2/4. It would be 1/2. And so that'd be 1/square root of 2. So that would be r. What would be theta? Well, remember, we're tan theta is a/b. So that would be 1/2. That would be 1. What quadrant are we in? Well, a and b are both positive, so we're in quadrant 1. So that would imply 45 degrees or pi/4. So when you walk through this, the representation that you'll see in the book will use radians. I'm going to use degrees. And the reason why I am is I think it'll be easier when you do these calculations, because at the end of the day, you'll want to walk through the polar arithmetic and then convert it back to the Cartesian form. And so I'll show you what I mean. So this is what the book's representation looks like. Well, r, they don't like to put the square root. All right, so it looks like this. Pi/4 plus I sine of pi/4. Here's how I'm going to write it. This would be 1/square root of 2. And what's pi/4? 45 degrees. So let's write it this way. Sometimes there is a convention, but I think the convention makes the problem harder. So I'm going to go to this representation. These are both exactly the same mathematically. So what do you first do? Well, if you take it to the 10th power, the first thing we want to do is do this to the 10th power. So remember, what does this look like? This would be 2, and the square root is 1/2, right? To the 10th power. And they used to, when you do that, will multiply. So it'd be 1/2 to the 5th, and that would be 1/32. So that is our new r. So what is inside here? Well, 10th power, we multiply each by 10, right? So that would be 10 times 45 plus I sine of 10 times 45. So you see what happens. And I think it's better. I like thinking in degrees. So what's going on here? Well, you're going all the way around 360. And then what's left? Well, another 90 gets us back to 450. All right. So a different representation would be if you subtract 360 from these, you would get the exact same equation, right? So you could rewrite it this way. This would be 90 degrees plus I, whoops, shouldn't be two cosines, right? That should be sine. Sorry about that. So that would be sine of 90 degrees. So what's cosine of 90? That's 0. What's sine of 90? That is 1. So this simplifies to just I. So what are we left with? 1 over 32 times I. So that would be 1 over 32 I. Whew. Super easy in the polar plane, super tedious, and I would consider hard because it's really easy to make a pretty simple arithmetic mistake starting to multiply all these fractions together. And so 1 over 32i is the answer for this 1/2 plus 1/2 I to the 10th power. Okay, so there'll be a couple of those to practice in your last homework assignment. And so let's talk about this idea of roots of an equation. And this is the Moivere's theorem. And so here's what it looks like. This idea of now finding the roots. And if you, I'll refresh your memory in a minute after I explain the formula. So the idea here is that in the complex plane, if you represent it in polar and you take it to the 1 over n power. So remember, 1 over 2 is square root, 1 over 3 would be cube root, 1 over 4 would be quarter root, etc. And each time you do that, what will end up happening is you'll end up with that many possible solutions. So when you take the square root, you're going to end up with 2 possible solutions, a cube root 3. And here's how you calculate it. The r ends up being 1 over n, which is nice. And then here is the iteration, where k ends up being the roots from 0 to n minus 1. So if it was cube root, it would be 0 and 1 and 2. If it was quarter root, which would be 4, it'd be 0, 1, 2, 3, etc., etc. And so here would be the representation. And you just have to walk through it in a step-by-step process. So let's go through a couple, let's go through a couple simple examples without using the trig to get started. So say like you wanted to solve the equation I minus I squared minus 9 equals 0, right? So if you solve that equation, you would have I squared equals 9. And then you would take the square root. And if you remember when we did that in the old algebra days, we put this plus or minus 9 here, all right? And so the answer would be plus or minus 3. So that's what we made, is you have 2 solutions, right? 3 times 3 equals 9, and minus 3 times minus 3 equals 9. So say like we changed that and said x squared plus 9 equals 0. How would you solve that? Well, again, you would bring x squared and minus 9. And then what did we do? Well, if we were in the complex plane now, and remember, that's what we're going to be in, since we're doing complex numbers, right? If you took the square root, what did you get? Plus or minus square root of minus 9. And so what was that? Well, remember, we rewrote it this way typically. And so what is that? That is I. So it would be plus or minus I and then 3. So it would be plus or minus 3I. So 3I times 3I is minus 9. And 3 minus 3I times minus 3I. So again, we have two solutions, 3I and minus 3I. And so you can see that when you do this, it's not too bad when you're dealing with square root. But let's do this problem. How about if you had x to the fourth minus 16 equals 0? Well, let's do plus 16, because that's what I have in my notes. Plus 16 equals 0. And you wanted to calculate x to the fourth equals minus 16. So then how do we do that? Well, now what you have to do is the 1/4 power, right? So this would be x equals minus 16 to the 1/4 power. And here we're going to get 4 solutions. And you will see that in the trig representation, it's just so much easier to do with regards to these calculations, and especially when the numbers start to get complicated. So let's do this one as an example. So if we take minus 16, all right, and how do we represent that in trig? Well, this is going to be here, right? Because this is real and this is imaginary. So what is this angle? 180 degrees, right? So that would be 180 degrees. And what's the R value? The R value is going to be 16. So this representation is 16 cosine of 180. You could put pi in if you want. I'm going to use degrees. I find that when we do the calculation, it's just a little bit easier. But you could do radians if you like it as well. And so that would plus bi sine of 180 degrees. Okay, so if you look at that representation, you just double check. And so cosine of 180 is minus 1. And cosine of, or sine of 180 is 0. So the I cancels. So that is a valid representation. And so now here's our equation. Well, we're going to do the quarter root as we were talking about here, right? Minus 16 to the 1/4. So here's our equation, w to the fourth. And so that would be r to the 1/4 power. And then what we want to do is cosine. And so theta is 180 degrees. And then we do 360. Okay, that's 2 pi divided by n, which is 4. And that plus I sine of 180 plus 360k. See what I mean? Instead of all those crazy fractions, divided by 4. And then what is our k? Since we have 4, k would be 0, 1, 2, and 3. So we have to do this 4 different times. Well, hopefully you'll see that 16 to the 1/4 power, what would that be? Well, if you got out your calculator, you would see that would be 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So that would be 2. So the good news is here is that this calculation here would be 16 to the 1/4 power, and that would equal 2. So let's just get rid of the 1 over 16 to the quarter and make that value 2. So now what is k equals 0? Well, when you plug 0 in, what do we get? We get 2, and then we get cosine of what? 180, 0 divided by 4, right? So that would be 180 divided by 4 plus I sine of 180 divided by 4. Okay, so here we get out our calculators, right? And we'd have 180 for divide. So this would be 45 degrees. And this would also be 45 degrees. Okay, so when you do this calculation then, it would be 2, and we're in quadrant 1, right? So this would be square root of 2 over 2 plus what? Sine of I times square root of 2 over 2. And so you see that these 2's would cancel with the 2 out front. And with k equals 0, you would get square root of 2 plus I square root of 2. So that would be with k equals 0. And you can see in this case, my whiteboard's going to get a little bit crazy. So with k equals 0, I'm just going to write it down here on my sheet. I square root of 2. Okay, well, unfortunately, I need some space here. So let me get rid of this. And let's make k equals 1, see what I get. So when k equals 1, again, we have 2 out front. And what do we have here? So we have cosine of 180 plus 360 divided by 4. See, that's why I like degrees in this case. And then that would be plus I sine of, again, 180 plus 360, again, divided by 4. So what does that give us? Well, get out your calculator again, and it's 360, 180 plus 4 divide. This is 135 degrees. All right, so now we're in quadrant 2. All right, so what in quadrant 2? Cosine is negative, sine is positive. So this would be 2. And cosine of 135 degrees is minus square root of 2 over 2. And sine would be positive. So this would be plus sine square root of 2 over 2. So you can see these cancel. And you end up with the second root of minus square root of 2 over I plus, I square root of 2. So when k equals 1, you end up with minus square root of 2 plus I square root of 2 for k equals 1. I know, very tedious, huh? It's even more tedious trying to do it in the Cartesian plane. So now let's pick k equals 2. We're halfway done. And so when k equals 2, what do we get? Well, again, we have 2 out front, and now we have cosine of 180 plus 720 now, right? Divided by 2 plus I sine of 180 plus 720 divided by 2, right? Because 360 times 2 is 720. So again, that's why I like this degrees. I get my calculator out. 720 plus 900 divided by 4 is 225, all right? 225. So in this case, where are we? Well, 225 is right here, so we're in quadrant 3. So both sine and cosine are negative. So in this case, you can kind of see what the pattern is now, right? So this would be minus square root of 2 over 2. And then this would also be minus I square root of 2 over 2. So you can see the third one would be minus square root of 2 minus I minus square root of 2. That would be k equals 2. And that would be minus square root of 2 minus I square root of 2. And you'll see on the other one, the positive one, we're going to be in the fourth quadrant, and it just flips it. So when k equals 3, we'll end up in the fourth quadrant. So, but let's do that last one. Okay, so let's do this last one. And so that would be k equals 3. And so that would be 2 cosine of 180. And k equals 3. So what is 360 times 3? 1080 divided by 4 plus I sine of 180 plus 1080 divided by 4. And so when you do this one, 180 plus 4 divide, it was 315. Right? So now we're at quadrant 4. And you would see that it would be 2. And then quadrant 4 cosine is positive, so it'd be square root of 2 over 2 plus I minus square root of 2 over 2. And so that would simplify to 2. These cancel again. And so it'd be square root of 2 minus I square root of 2. And so these 4 roots would end up looking like this. K equals 0. It would be square root of 2 plus I square root of 2. K equals 1 would be minus square root of 2 plus I square root of 2. K equals 2 would equal minus square root of 2 plus I square root of 2. And the fourth root would be when k equals 3. It would be square root of 2 minus I square root of 2. So if you would take any one of those numbers to the fourth power, the answer would give you minus 16. So that is really kind of the strategy with regard to that. So I wanted to do this one all the way through. And let me just show you another one that you don't have, you could probably kind of do in your head. Say like you wanted x squared minus 16 equals 0, not squared, to the fourth power. Minus 16 equals 0. So that would be x to the fourth equals 16. So what do we know? Well, 2 times 2 times 2 times 2 equals 16, right? So that would be one answer. We also know minus 2 times minus 2 times minus 2 times minus 2 equals 16. That would be the second answer. You would also, trust me, but if you did all these 2i's, that would also equal 16. And guess what? The minus 2i's also give you minus 16. And so that's again what we mean by roots, is that if you take all these and multiply those together, the number of times, you would do that. And so the uh, the polar representation of 16 would again be 16. And then in this case, it would be cosine of what? It would be cosine of 0 plus I sine of 0. And so if you walk through that calculation with n equals 4 again, you would see you would get these 4 answers. So I'll let you to do that as practice. I could do that in our Zoom class as well. And so that ends the recorded lecture for section 5.3. Finish in with an important theorem called de Moivre's theorem.